Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Mike Brown with us today. Hello, Mike.
Hey, so fun to be here. Thanks for inviting me.
It's so nice for you to be here. And Mike, what's your geolocation?
I'm in Pasadena, California, home of, I don't know, 95% of astronomers in the world. Who knows? Some huge number of astronomers are around here.
I don't know. CFA might have something to say about
CFA, Tucson, there are a few in a few other places. But it
uh,
seems like you can't walk down the street without accidentally running into an astronomer around here.
bumping into one. Absolutely. Very cool. Very cool. And so do we have the beautiful sunny California weather today on this June?
It's June. So if you've been in Pasadena in June or Southern California, it's June gloom. So in May and June, we generally have cloudy morning skies with a thick marine layer, and sometimes we never see the sun. So it's cold.
Ooh, chilly. I think maybe some of that marine layer is coming over to Phoenix here because we definitely have an unusual high clouds today.
Yeah,
So
if you can take some of that away, we could actually use a little sunshine. It'd be nice.
cool.
I say that until about July when I say, "Oh my God, too much sunshine," and then
Time to go.
never perfect.
Very cool. You got some cool rocks on your decks there. What are those?
Oh, I have way too many. But let's see. From my favorite one.
Hey.
I always, if you walk into my office, I will quiz you on rocks because I'm actually in a geological and planetary science department, so I have a lot of geologists come walking in my office, and I will often hand them a rock. Sometimes I'll hand them this one. And
Ooh,
I'll say, "What do you think this is?" And if you hold it, if you look at the back of it, it looks kind of like a meteorite because it's a
yeah,
meteorite,
kind of
and
dark.
it's heavy, so it's clearly an iron meteorite, but it has crystals and
Sparkles in it.
if you look inside there, you realize that they're green and they're sort of dark. So they're olivine and pyroxene, but it's surrounded by, let's see if I can get a good reflection. Yeah, you can see it's iron. It's a nice shiny iron.
Cool. Yep. Mhm.
So it's a palisite, which is, I think, one of the most cool meteorites that you can have because it's got iron, so it came from the core of a little mini planet, but it also has crystals, so it came from the mantle also. So this is the core mantle boundary of an exploded mini planet,
Love
which
it.
I don't know, that's about as cool as it can get.
That's very cool. That's
I
awesome.
have one right here in my hand. It's pretty cool. Some exploded mini planet somewhere.
So does that one have a name? Did that come from a particular meteorite or?
The pallasites are sufficiently uncommon that everyone comes from a named one. This one came from I believe it's Kansas. I think it's called the Conundrum.
Okay.
And as pallasites can be very expensive because they're beautiful, but this one is on the cheaper side because this one rusts. And so the one thing they said when I got it is like, whatever you do, don't just leave it out on your desk and hand it to people. But like, this is what it's for. It's to hold people and to show people how cool it is. And someday the rest I'll be sad, but it's a beautiful meteor. I have like fancier ones. Here's some more pallasites, which you can actually let's see if you can.
Ooh, that's nice. Very nice.
They're translucent and they're in a nice little box. So
Yeah.
I do take them out too. I'm not. They're for people to hold and to talk about.
And be wondered by, and
That's why they exist.
you can always take the rust off, right? Well, I don't know,
Not
easy to do. Very cool. And Mike, what do you like to do for research?
I do a lot. I do a lot of different things because I'm the typical stereotypical scatterbrain professor type. So, it depends on the day of the week. But one of the things that I have just really been excited about for pretty much the entire time I've been doing astronomy is just exploring the outer part of the solar system.
Cool.
And it really is just it's exploration in many ways. It is a part of the solar system that we just don't know very much about, and we're just learning more. And as you learn about it, you're sort of learning about the early history, how the solar system put itself together, how planetary systems put themselves together. So I just think it's fun.
Cool. Very nice. And that is going to bring us to this very lovely AJ article. It is open access. It's the open access era. People, go grab a copy for free. Get one. A Pan-STARRS 1 search for Planet 9. And Mike, take us away.
Okay, so this was a paper long in the making, way too long. This was one of those papers that started before the pandemic, and pandemic kind of slowed
Wow.
it all down. And but this was one that I worked on with Matt Holman at the CFA and Konstantin Batygin, who's 3 doors down from me right
Hmm.
now. And the goal was, at this point, most people have heard of the hypothesis of Planet Nine existing, and the
Yep.
goal is to find it. And this paper was attempting to find it using the pre-existing Pan-STARRS 1 survey, which is really the best large sky survey that goes, it doesn't go particularly deep, but it goes moderately deep and covers the sky multiple times. So it's if you're going to look for for Planet Nine, something like that is the ideal way to do it.
Cool. Cool. Okay. Let's talk.
So,
Go ahead and get into it, and
all
let's.
right. So it's always fun to start these papers because when you talk about a planet beyond Neptune, you get to go back to papers like Babinet 1848 as your first reference. The idea that there are planets to be found beyond Neptune really started almost immediately with the discovery of Neptune, and it's
Mhm.
anytime anybody found some slight perturbation that they didn't understand, or they had bad data that they thought led to a slight perturbation they didn't understand, everybody would jump up and down and say, "Oh, I just found a planet. There must be a planet out there." There are dozens and dozens of these predictions of planets beyond Neptune, maybe planets inside of Mercury, planets all around the solar system that we
Mhm.
haven't found. And every time that happens, it's been wrong. And it's been wrong either because the data are wrong and
Yeah.
the phenomenon that the astronomers were looking at is not a real phenomenon, or because the physics that the astronomers used to predict the existence of a planet, they got that part wrong. I mean, the famous
Yeah.
one being Leverrier predicting Vulcan inside of Mercury.
Yes.
We'll give him a pass on that one. He didn't understand general relativity back then, so um, it's fun to talk about that because once again we're at this stage where we have predicted the existence of a giant planet beyond Neptune, and the easiest thing to do is to say these guys, like everybody else, are either their data are wrong or their physics are wrong, and
Right.
I think we've done a pretty solid job in these last 8 years now
Yeah.
of making the case that it's hard to refute the observations. There are multiple lines of evidence that there is something out there, and if there's not something out there, there have to be 5 or 6 separate phenomena to explain all
Right.
these things that we don't understand otherwise, and we don't know what those are. And the physics, these days, I think we're pretty good at getting the physics right. So I think the answer is there's some large gravitational force out there that we need to go find. And then, there are sort of the fun explanations, like maybe it's a primordial black hole,
Mm.
which, maybe it's
Maybe.
all we can tell is that there's a mass out there, a
Yeah.
concentrated mass. And so sure, could be a black hole, could be a burrito, could be a large cat. Uh, all of these things could be true, but it's a planet. What I like to explain to people is that a planet is actually a mundane explanation, and that's one reason why it's probably the right one. Like the idea that there are other planets in our solar system, although to us it's still a little bit mind blowing because we haven't thought about it in such a long time. We see other planetary systems with planets very similar to this
Yep.
out there in the galaxy. The idea of something, it turns out that we think that it's something like 7 Earth masses. The idea of a 7 Earth mass planet is not only not surprising, it's like one of the most common things that stars have. So the idea that it has to be something strange like a black hole or some other
Yeah.
weird phenomenon um, really is not necessary. It's probably just a planet. And so as long as it's just a planet, we need to go find it. So there were some earlier papers that we had written trying to use the current observations to predict properties
Yes.
of the planet. And that's a really important part of this paper because we need to know what we're looking for if we're looking for a planet out there. I mean, we could just look through the entire Pan-STARRS data set and look for anything that's really far away. But that turns out to actually be very difficult, just because even searching the more limited space that we looked was took many months. I think it took like 9 months of the computer spinning before it finished this
Wow.
search. So,
Okay.
and that's, as you'll see in a minute, that we did a pretty limited thing. But the way that we figured out where to go is we used the current observations of, in particular, the structure of the Kuiper belt, the very most distant objects in the Kuiper belt, these objects that are on extremely eccentric orbit,
Mm-hmm.
eccentric orbits that are being modified by Planet Nine. And if you look at those objects, those are the ones that are all clustered both in the direction that they point and also in their pole position. So they're clearly this strange population being affected by something we don't know about. And if we can, we then do large numbers of n-body simulations of different properties of Planet Nine. We make it a little more massive, a little less massive, more eccentric, less eccentric,
Right.
tilted this way, tilted that way, and ask, which of these best matches the current observations. And we do that, in a rigorous statistical way, and we then have properties of Planet Nine. So this earlier paper that we had back in 2021 gave us parameters, predicted parameters of Planet Nine, orbital parameters, mass, brightness, distance away, all these different things. And that allows us to go start looking for Planet Nine.
Nice.
So the interesting thing is, I think, it gives us a position in the sky, and it also gives us a brightness. And so a lot of people outside of astronomy, when they say, well, what do you just like look through all these positions in the sky? And the answer is no, you don't do it like that. I like to think of it as you're mowing the lawn like you would on the sky, but you're first starting at the bottom part, and by bottom I mean the smallest magnitude, the brightest objects.
Right.
So the first thing you do is look for the easy stuff. So we had predictions that at the very extreme end, it could be so bright that you could find it with something like ZTF at Palomar.
Mm-hmm.
ZTF, if it were something like 20th magnitude, 20.5, ZTF should have been able to find it.
Yeah.
So we did this big survey with ZTF, didn't find it. There was a nice existing survey, the Dark Energy Survey, which covered only, it's much deeper than any of these other surveys, but it doesn't cover very much
part of it. Yeah.
Space. But we used the Planet Nine, the Dark Energy Survey, to rule out some more of that. So at this stage, before we started out looking at the Pan-STARRS data, we'd rolled out about 60%. There it is, 61.2% of
there we go.
Of our parameter space of where we think Planet Nine should be. And Pan-STARRS is going to cover a significant chunk of the remainder of that. So we were pretty excited to be able to get this. So cool. There are some great things about Pan-STARRS, and there are some terrible things about Pan-STARRS. And if you work on Pan-STARRS, you will agree with the statements about the terrible parts. The great things about Pan-STARRS is it's a nice modest depth, 21, and some change in some good bands that you would care to look for things in the solar system. R band, I band are really our favorite ones. It goes moderately deep in those bands. It covers something like 3 pi steradians of the sky, so really the entire sky above about minus 30 degree declination, and it covers the sky multiple times, depending on where in the sky. You can cover it. I'm going to forget the exact numbers. The Pan-STARRS people remember the numbers, but they can be covered dozens of times over the years and in the different filters. And if you are a planet in the distant part of the solar system, what that means is to Pan-STARRS, you show up as a one-night transient.
Yes. Okay.
And then you might look at the same point in the sky 2 weeks later, 2 months later, something like that, and there's another one-night transient.
Yes.
In the sky, not in the same place the first one was. And that's what Planet Nine looks like.
Okay.
Pan-STARRS. The reason why this is particularly hard, though, is because if you go to the Pan-STARRS like user page on how to use Pan-STARRS data, Space Telescope, one of the things they say is whatever you do, don't use one night transients for any science. And the reason is because the detectors are,
Okay.
the detectors just have a lot of spot noise, of just like
Yes.
random
Mhm.
little sort of salt and pepper, maybe not the salt part, the pepper part. Like they're just full of single night,
Like
single
that.
observation garbage. And the way you use pan-STARRS data is you ignore anything that only shows up once. You use the things that show up multiple times,
Yes.
and which is great. And that covers nearly all of the science that everybody wants to do, except for me. I need one night detections, and so we had to use them. So we went through and found all of the one night detections,
Okay.
and there are 1.26 billion of them.
Woo.
And 1.2599999999 of those 1.26 are garbage.
Yeah.
And so, and it might even be the 1.26 are garbage. Um, and so we are looking for any of those that we can connect on a Keplerian orbit. And that's the nice, everybody has a filter they use to find their objects. Ours is a really great filter. A Keplerian orbit is a fabulous filter for trying to find an object, because you can't kind of fit a Keplerian orbit. You can't, fit one some days and slightly not fit it the other days. Like it is, you don't know what the orbit is, but if I give you 4 points, you can tell me yes or no, this fits a Keplerian orbit. It doesn't mean it's real. Maybe it's just randomly, but eventually you have to have, objects will fit this Keplerian orbit. So that's our goal. Find any objects that fit Keplerian orbits that are beyond about 200 AU. So how would we do that? The first thing we have to do is just get rid of a lot of the garbage, as much of the garbage as we can.
Right.
And there's a whole part of this paper where we go through on trying to find regions that are worse than others. We look at the other single point transients are asteroids, and most of those are known asteroids, and so we ignore those. But we use those as tests. Like, what is a real? We know they're real because they're real asteroids, and so we can look at what a real asteroid looks like versus some of these other random spots, and that gives us a few parameters that we can use to get rid of some objects, and that gets us down from whatever it was, one point something billion to something like, there we go, 772 million. Still a lot of potentially false things there. We do things like look at bright stars. Bright stars make a lot of garbage around them, and so the easiest thing to do is just find regions around bright stars and exclude them. And we then, even the many different detectors have noisier regions and less noisy regions, and we clip them. And so in the end, we with getting rid of things with strange parameters, things that are on bad parts of the chips, things that are nearby near stars, we end up with something like 314 million single night detections.
Okay, here we go.
Still a lot. Okay, still a lot. And the final thing we do is we realize that if you just look at individual pan-STARRS image, not the images, but just the detections from a single image, just for whatever reason, sometimes there is a cluster of single image detections because of some detector problem or sky problem, or it's we don't even know what the problem is, but it doesn't really matter. Just realize that there are just a lot of objects in one spot. We cut them, and finally we're left down to 244 million objects. This is still
hefty.
So our goal is to say, in this 244 million objects, are there any that you can connect the dots and say these fit on a Keplerian orbit?
Awesome. I'm with you.
Okay. So when you're doing that, one of the things you have to really worry about is how sensitive are you, both how sensitive are you to real to things of certain brightnesses, but also how much of all this cutting hurt your sensitivity to finding things. We just cut a lot of things.
Right.
I can't guarantee that some of those things we cut weren't real. Probably some of those things that we cut were real. And one of the ways, the really powerful way that we came up to calibrate this transient survey is to use our known transients. Our known transients, our known single image transients are asteroids.
Okay.
So we went and looked at something like 500,000 numbered asteroid. Numbered means that we know their positions well enough that we can predict exactly where they're going to be at any point in time. And during that 5 years of the Pan-STARRS survey, we went and looked at every single image that was taken and looked to see if that asteroid was detected or not. Again, we didn't actually do this in image space. We just did it in catalog space. So we looked at the catalog from every single image, and we say, hey, in this image, there should have been these asteroids detected. Were they detected? Were they not detected? And then we kept a record of that based on magnitude. If it was, might have been a bright asteroid, easily detected, might have been something that was predicted to be 25th magnitude, shouldn't have been detected, wasn't detected. That's really good.
Cool.
In the end, that gives us, in each area of the sky, it gives us a night to night to night magnitude limit, basically, of what we detect and a probability of detecting things based on magnitude. And it's nice because it's not just this is the magnitude limit.
Yes.
It also says it takes into account things like if we're in a dense star field and we have a lot of regions that we have clipped out because they're bright stars, well, that's going to drop our probability of finding even a bright asteroid.
Indeed.
And that shows up in this calibration. So every single location in the sky, we have a probability as a function of magnitude that you would be discovered.
Okay. Yep.
And that's great. So now we have a very good calibration, and that you can actually see that calibrated magnitude limit, I think, in Figure 1, which doesn't appear on this page, but it appears.
Figure 1. Here we go. V-band.
Yeah. So this is the probability that there's a that there's a 95% chance that you would find a moving object 9 or more times. This is actually the other important part of the calibration. It's not just one night. It's saying, okay, would you find it any 9 times? And the number 9 is as we'll talk about, it will end up being an important one. That's going to be the number that our requirement. To find planet 9, we would need to have seen it 9 times at any point in the sky. And the probability, 95% probability, you can see here, and it's pretty good. And the red areas are about 22nd magnitude. See these regions, those bad regions, that's the galactic plane.
Yep.
Northern galactic plane is bad. The southern galactic plane is my nemesis. There's really not enough good Pan-STARRS data in the southern plane. Actually, interestingly, we do better in the galactic plane in ZTF. Even though the overall limit in ZTF is not as good, the fact that ZTF covers the northern galactic plane like 90 or 100 or even more times, that was even in the first couple of years, lets us get through all that confusion and eventually find things. But this is our limit. So we're looking at, planets 9 to 22nd-ish magnitude, except in the galactic plane. That's at least our hope. If we can figure out a way to find all Keplerian orbits that have 9 or more detections. And so then the question is, how do you do that? Because Keplerian orbits are weird. They make these big retrograde loops year after year after year. If you have an observation one night and the next night, it's easy. You say, oh, it's that one. It moved from here to here. Boom, easy.
Good.
Have an observation one month, and the next month, and it's moved an arc minute maybe or more. It's a little harder. If you have an observation a month, and then next year, and then next year, and there are 280 million other transients around and through there, that gets really hard. It's a powerful filter, but the figuring out how to use that filter is hard to do. And this is a problem that was the technique was it was just a super clever technique figured out by Matt Holman. It's one of these things where you read the abstract of the paper before you even read the paper, and you read the abstract, you're like, oh my God, that's just the hardest thing I've ever thought of. I've never thought of, someone else thought of.
Cool.
It's this incredible insight that seems silly and trivial when you first say it, but it's brilliant, which is that an orbit in the outer solar system, anything in the outer solar system, year after year, it goes like this: retrograde loop, retrograde loop, retrograde loop.
On the sky,
It changed the orbital parameter slightly. It totally changes the look of everything.
Okay.
However, you happen to be sitting on the surface of the sun. I don't recommend that, but if you
No.
were, what does an orbit of an object look like? It looks like great circles. They
Yes.
just look like great circles. And in particular, as you move to the outer part of the solar system, where you're not worrying too much about changes in heliocentric distance with time because they're moving
Yes.
slowly, it really is just a great circle at a constant angular velocity.
Mhm.
And so that's a brilliant insight if you could then figure out how to put yourself on the surface of the sun, which is a little harder. But what you can do is you can assume a distance for every one of those 288 million transients, assuming it's at a certain distance, let's say 500 AU.
Okay.
If it's at 500 AU, we can do the geometry. You know, we saw it from the Earth.
Done.
We're looking this direction. If I were on the sun and I knew it was 500 AU away, you can triangulate and say, oh, that means it's from the sun, it would have this heliocentric longitude and latitude. So you transform your entire data set into something that is at an assumed distance, 500 AU.
Mhm.
Now it's a much easier.
I'm with you.
You're looking for straight lines. You're looking for things moving in straight lines at a certain angular rate. And technically, the way you do it is you actually calculate the angular rate between one object and every other object in your survey and look for clumps. If there's a clump of, we said there need to be 9 objects. If there's a clump of 8 other objects moving at the same angular velocity, that might be your object.
Cool. Okay.
If it's not a clump, there's nothing there, or you got the wrong distance. So then you have to sweep through a whole range of assumed distances. That's the trade-off. You don't get to know the distance ahead of time, so you have to sweep through that range of distance.
Okay, I can see where the compute's coming from. Yes.
Yeah. So
Yeah.
the good news is, once you find 9 or more objects in a clump, your clump was pretty crude. You weren't actually really fitting for a Keplerian orbit at that point. You were just looking to see if anything was plausible.
Right.
But once you have those 9 objects, you can fit a real rigorous, least squares Keplerian orbit, look at the residuals, and ask whether it has a reasonable chi-squared, whether it has residuals that are too big, and if it's real. And if it's real, you just found planet 9. But not really. And here's why. Because this is a big, complicated process that there are a million ways to screw up when you're coding. Trust me, I at least a tenth of a million ways when I was coding it all up.
Yeah.
And it's hard when your job is to look for one object in the sky. Don't screw up your algorithm, because then you'll miss it. And when there's a good chance you're not going to find it. So the only way that made any sense, the only thing that made any sense for us to do was to inject a synthetic population into our catalogs. So we had, in this previous paper, we had already created what we called the Planet 9 reference population. So this is something that we made for use by anybody who's looking for this planet, which is 100,000 objects sampled from our distributions, which statistically represent Planet 9, where it is in the sky, how it's moving, how bright it is, anything else and it has the reference population is the set of objects with a certain position on a certain date.
Okay.
And therefore you can fast forward it to any position, to any date that you want, where you happen to have an observation, and say, yeah, this object is the same as this object, is the same as this object, which means if I go do a survey and I rule out certain members of the reference population, saying I never found those.
Right.
Well, you don't have to then go back and look, oh, but what about over here? Like, oh no, those were the same objects. So you're ruling all these objects here. So this is what we did in ZT. We ruled out this population, some of this population. This is what we did for the dark energy survey. We ruled out some of this population. And here we took all 100,000 objects. They range in magnitude of our entire predicted magnitude range, which is something 19/20th magnitude to about 24, 25.
Cool.
We took every single one of those objects and we injected them into the Pan-STARRS catalogs.
Yes.
And the way we did that is, if you remember, we had our calibration that the probability of detecting an object at a certain magnitude.
Yes.
So our synthetic population has a magnitude. Every spot in the sky has a probability for that magnitude. So we would say, okay, here's an observation. Are there any Planet 9 reference population members in this observation? Great, they are these magnitudes. Let's randomly decide if they were observed or not observed.
Cool. I'm with you.
So at the end of the day, we have a set of real pan-stars observation and a set of 100,000 synthetic objects, of which I'm going to forget the exact numbers, but it's like if we let's see where we are in the paper now.
Results.
I think actually we came down because we were doing figure 1, which showed up late. So if we go back up to we talk about the reference population. Let's go. Go up to the next page, I think.
Oh, I'm sorry. Okay.
That was talking about calibration. Yeah, here we go. We talk about the reference population here.
Right.
And I was just trying to remember the number because I didn't have the number off the top of my head. But the reference population also tells us that we don't have to look at the whole sky, because the entire sky does not appear. The reference population doesn't uniformly cover the sky. It uniformly covers that. So that tells us where we look in the sky. Okay. And we looked at the part of the sky where 99% is. And I was trying to see if I had a number in here that told us.
Yeah, I'm looking.
I don't. But there's some number that we'll come to in a minute of the reference population. So we take the whole data set and we run it through that algorithm that I talked about.
Yep.
And when we do it, we find a couple things. One is we first try it. The smaller number of objects we can require, the more sensitive we are. If we could do this survey by only requiring 1 detection, we'd be super sensitive, but that's kind of dumb. We tried 7, and when we tried 7, we were overwhelmed with false positives.
Okay.
Basically, what that means is that the probability of having 7 randomly positioned points in your 280 million garbage detections, you will find a large number of things which still fit a Keplerian orbit. Okay. And that's just because 280 million is such a big
number. You're going to find something.
In the end, we realized that we had to even 8 was too many false positives, and 9 did not overwhelm us with false positives. So 9 was the number we ended up using.
Okay.
When we ended up using 9, we found a lot of objects, and of those lot of objects, they were all the survey things that we'd injected. Oh, I talk about a little bit about the processing in there. The nice thing about the survey is if you break it into little blocks in the sky, it's nice. It's trivially parallelizable, which is why it only took us 9 months of processing instead of 900 years. It was still there. It is. We added 69,080 reference members had 9 or more detections.
Very cool.
Survey. And we found 68,550. We found 99.2%. That means
good.
The algorithm is fabulous. I mean, it really does. It's an impressive algorithm, and I credit again the insight of Matt Holman, who just pulled it out of his brain one day, and then
nice.
It's just so cool that you can actually use it this way. It's an incredibly efficient way. We would otherwise the other ways that people use to try to find things are like, here's an object, here's another object, here's another object. Let's see if they fit a Keplerian orbit. Let's look for things. It's like that is just intractable algorithm. This is fantastic. Yeah. So it's a great survey. It's incredibly efficient. And if Planet 9 were in there, we would have found it. And as you see on the next page, Planet 9's not in there. There is no Planet 9. We did not find anything that was real. We did find 909 other linkages that had 9 linkages, and each one of those was one that was like 7 or 8 pieces of garbage, and one of the things that we had put in. Actually, it was usually like 6 or 7, because the things we put in fit Keplerian orbits. So in the end, we did not find anything with the predicted characteristics of Planet 9.
Okay. All right.
And that's sad. I actually thought this one was a good chance. I was pretty optimistic that we might find them.
Gold.
In the end, that was something like 17,000 additional objects we had not already ruled out from ZTF and dark energy.
Yeah.
So what this means is that something like 78% of the reference population has been ruled out.
Ooh, bummer.
And
Okay.
that's a big number, but not a huge number. You know, you would
100%.
you would hope that if you surveyed, if you knew an object was somewhere randomly in the sky and you surveyed randomly 78% of the sky, you would think there was a good chance of finding it. In fact, you would think there was a 78% chance of finding it.
I would.
And you'd be right. But if you don't find it,
doesn't mean it's not there.
Still another 20% that we don't go. So instead, in this paper, we talk about the limits and we show what more there is to see. And figure 3 is a good one of it, which just shows you the magnitude limits at different points in the sky. Actually, before we go to figure 3, let's go back to figure 2 because actually that's going to be relevant for figure 3.
Oh, yeah, here's all of them. Yeah. ZTF.
Combined.
Yep.
Combined V magnitude limit, along with a nice typo for the word survey right there. That's cool. Right there. This is the real version. You would think that the editors would have caught that.
Caught that. No goodness. Okay.
So it's pretty good. These are the magnitude limits. That weird little chevron you see on the right side. That's the dark energy survey. It's not much of an area, but it's quite deep, so it covers all that in through there. If you remember, pan-stars didn't do so great through the galactic plane, but where the galactic plane is, that's ZTF coming in.
Yes.
And the dark blue section down there has never actually been seriously surveyed. The very southern part of the sky, where Planet 9 could be as bright as 18th magnitude. I don't think it is. I think we would have found it by some other accident if it were really that bright back there. But nobody's ever systematically looked for that little swath below minus 30 degrees. And, the Southern Galactic Plane, again, is my nemesis and has not been surveyed well. There are other reasons for thinking it's not in that region. It's the Southern Hemisphere is where Planet 9 would come to perihelion. And it would be bright enough and close enough that if it were there right now, I think we would have seen it in the planetary perturbations between Earth and Saturn that were measured by Cassini.
Yes.
So I think I'm not too worried about that region there. Where I think it might be, let's actually go to figure 4 instead.
Yeah, let's go slide down to figure 4, and here's what's left.
This is what I like to call the treasure map. It's been my version of the treasure map for every version of it, but this is the latest version of the treasure map, which is where Planet 9 might be. Here's why, and it's because this is now the probability density function of the remainder of the reference population that no survey would have found yet.
Okay.
And you can see where things are good. Again, there's that chevron, that dark energy survey chevron, where you don't see anything because dark energy survey would have found everything there. You have pretty good through the middle of this figure because that's where pan-stars is quite sensitive, and also where Planet 9 is not quite as far away. Planet 9 comes to perihelion close to the southern galactic plane and is at aphelion close to the northern galactic plane. Well, that whole bar near the aphelion. So it's both furthest away and faintest.
Yes.
Therefore, it's beyond the magnitude limit of pan-stars. So that's where to look. It's either that region, the faint region where pan-stars, it's too faint for pan-stars, or again, if you look in the southern hemisphere, the southern galactic plane and that little part of the southern hemisphere, we have not looked. I think it's not there, but anybody who's got a nice telescope sitting down there looking for something to do, check out the treasure map.
Go to the treasure.
I'm happy to tell you the right way to do it. It would be a cool thing just to double check. But that's where we're looking. That rectangle there in the northern part of the sky is where we need to be looking. And now we can go back to figure 3,
Okay.
which shows you what those magnitudes are, what we've ruled out, what fraction of each magnitude we've ruled out. As you can see, you know, up to 21st magnitude, and this is if you exclude the southern galactic plane, where I think it's not, and then you exclude minus 30 declination, where I think probably not. You look pretty good, but if you even without that, it's still pretty good. We do pretty good out to about 21st magnitude, 21 and some change. And then we drop off pretty fast. The only reason there's anything greater than about 21 and some change is dark energy survey.
Yes.
So all of that region, you know, dark energy survey covered about 20% of parameter space where it in the faint end. But there's a lot left to look in the faint end. And that's look. And so let's go back to figure 4, because I think that's actually the one to sort of end on, because that tells us what we need to do. It tells us two things we what to need to do. We need to go, as you could see from figure 3, we need to go to about 24th magnitude, and we need to cover this region there. Now, if there were a telescope being built that would cover the sky multiple times to 24th magnitude in that region,
for example,
that would be really nice. Do you have one? Anybody have one?
Oh, I could maybe imagine a few I could just randomly pull out of the air. Let's try maybe LSST or Roman.
So this is the LSST sweet spot. As long as LSST does that northern ecliptic spur that it has to do, telling you that now, it'll find it. If it's with the caveat that we'll really end on, and LSST, Vera Rubin Observatory, will find it. There is part of parameter space that's too faint. It could still be too faint. It still could be a little too far north for the northern spur if it's in those regions that you can barely see that are just a little too far north there. But really, most of that parameter space, and even the southern parts of the parameter space, this will be covered by Vera Rubin. And so when we first talked about Planet 9 8 years ago, people would say, what about Vera Rubin? And I'm like, oh, we're not going to have to wait for that. We're going to find it long before then. Turns out I was wrong.
Oh, well.
So not surprisingly, I am super excited for Vera Rubin to come in. People always ask, if it's not found by Vera Rubin, does that mean it's not there? And the answer is, I think that sadly, or happily, one of the two, happily or sadly, no, we can't. I don't think we can say it's not there if Vera Rubin doesn't find it. Here's why.
You didn't find it. That doesn't mean
I mean, even if we ruled out this entire reference population, there are a couple things. One is, a planet remains the best explanation for a large range of phenomena that we see in the outer solar system.
Yes.
Until we have a better explanation. I think the explanation remains that there's a planet out there. But the worst problem is all of our reference population predictions are based on one set of assumptions about the initial conditions of the early solar system. They're not a crazy set of assumptions. They are a set of assumptions that everything we're seeing related to Planet 9 came from a very massive extended disk of Kuiper Belt objects. And those are the objects that are left over that we're seeing.
Yes.
That might not be true. It might be instead that we're seeing Planet 9 pulling in objects from the Oort cloud and affecting those. And the bad news is it doesn't do that as efficiently. And when we see the efficiency of what Planet 9 is doing, we read that as being, here's how far away a planet is, and here's how big it is. If it's pulling them in from the Oort cloud instead, it has to be more massive to do that. And you'd think, oh, great, more massive, that's cool, we can find it better. Easier. But it's not good, because to be more massive, it also needs to have to be further away, and that actually hurts worse. And so you could push it out into the 27th magnitude limit, and that becomes really hard. And it becomes sufficiently hard that I'm not sure optical observatories is the right way to do it anymore. And we may have to go towards trying to find it from thermal emission in things like cosmic microwave background observatories, which is the next thing coming up. So I don't know. I have my fingers crossed for Vera Rubin, and I'm quite hopeful. But in the back, my paranoid side worries that it might be even further away and we might not be finding it. But, you know, stay tuned. This is coming up very shortly, and we should really know if it's out there, findable by our best optical observatories, or if we're going to have to keep searching in the radio.
Astronomy in real time.
Yeah.
Soon.
Exactly.
That was awesome. Mike, thank you so much.
Oh, thanks for this. It's fun to get a chance to
Very
talk about
lovely.
this in detail.
Yeah, you know, because we so rarely actually get to talk about our articles. You know, it's a unique opportunity.
Yeah.
Very
Yeah.
cool. Very cool. Well, I was going to ask you what holds the future, but I think you covered that pretty well on other wavelengths, other surveys. So let me just generally then, so VRO goes up. So when do you estimate with current techniques that we will move that needle from 76% to greater than 99%?
So,
2 years
Vera
away?
Rubin, let's assume Vera Rubin really starts a year from August. I think that's the
Yeah.
latest.
Mm-hmm.
You know, the real question is how long does it take before it's doing a real transient survey? Let's say a couple
Fair
of months,
enough.
but basically from the day it starts doing the full sky transient survey, you know, from the day it starts doing the real survey that we all think of as the LSST, 1 year from then, it will have covered the whole sky that it's going to cover, and that's enough. We don't need 10 years of data. We just need to see it a few times, as we've seen, and that's it. So it'll be one of the early results from Vera Rubin.
Sure.
Particularly if it finds it, it'll be, you know, you can just shut the
Cookie
telescope
Mountain.
on after
There's your
that. There's
mountain.
nothing as good as that, so it won't even matter anymore.
Very cool. How about things like Roman?
So it's Roman is you know, is a wide field of view for something in space, but as a blind survey of a big chunk of sky, it's just not going to be the one to do it. It's going to, you know, if you wanted to find a lot of things in the outer solar system, you can certainly point Roman and you have a big field of view and you go very faint and there will be a lot of little things out there.
A lot of little ones.
But if you're looking for one giant whale, that's not the way to go find it.
Okay, cool. Awesome. Very good. Mike, thank you so much once again.
So much fun. Thank you.
And I wish you luck in your search. I actually hope you find it.
Yeah, thank you. Or somebody.
Yeah, somebody,
Anyway.
one of those southern hemisphere telescopes. Go
Yeah.
for it. So that will do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.